My name is Alan Willard, and I will be giving the Programmable VFX with Unreal Engine's Niagara talk today. So for those of you who weren't in the previous talk that I gave, I'm Alan Willard. I've been at Epic for about 20 years now, and part of what my job is getting to demonstrate exciting new features for anybody who's interested. So let's go ahead and start. So what is Niagara? Well, it's our replacement for a number of things. The primary one being Cascade. It is Unreal Engine 4's next generation visual effects toolset. So what we started with was looking at our design philosophy, determining what that was, moving forward from that into what does a new system look like? How does it go together? What is the workflow for that like? How does that change any paradigms we use in deciding what our tools look like and how we work with things? I'll show you some of the UI and UX that we've created to not only create the tool set, but also improve the workflow for our artists and designers. And finally, there'll be examples of some of the new Niagara content spaced throughout the talk. Oops. So to start with, why are we building Niagara? Why are we doing this? Well, Cascade has been part of Unreal Engine since Unreal Engine 3. And since then, the engine has grown dramatically, both in terms of its feature set, but also how it's used. It now touches almost every industry, from art visualization, marketing, product creation, games, design, and more that we don't even know about. Our users themselves are more diverse. We have people coming from all jobs, all fields, becoming interested in the engine and how they can use it. And we no longer know what the best choices are for our users. So that's why we take feedback, and we're working very hard to make the tools very flexible, because ultimately it's the time that we can't put into the tools. We have to improve how you spend your time. Cascade has, as I said, been an extremely successful tool over a very long period of time. And there are things that have worked very well with that. You can see in this example the basic tool front for creating a particle system in Cascade. And it certainly had a lot of upsides. It's very fast to add behavior. The modules in the stack that you see here are created by engineers. They work very well together. And it's very obvious when you're looking at it that it's part of the stack for that particle system. So you can see that it's having an impact. They also work well together. There are very few cases where modules don't cooperate nicely. Artists who don't have any engineering background are able to create lots of detailed behavior using these pre-created modules, and having them in this stack paradigm of being able to see a vertical stack, including all the modules, makes it very easy to see what is contained in each of these sub-emitters. So Cascade certainly has clear upsides, but as with any tool, there are downsides as well. Each of these modules and the particle systems themselves are completely fixed function, meaning whatever data is necessary for any feature in Cascade is always contained in the particles, with very few exceptions. what that means is that even if you have an extremely simple particle system, the amount of data that Cascade is putting into those particles far exceeds the actual needs of the particle system. Anytime we add a new feature, it makes that problem a little bit worse because we're adding more data to that payload. We can't access that data from other modules. I can't tell the velocity to change based on the size unless I write an entirely custom new module. So being able to share data between particle systems or even within a particle system between modules is very difficult. Events within Cascade are very limited. You can call for an event to happen on collision, death, or birth, and that's basically it. You can spawn particles or destroy them when those events occur, but you can't arbitrarily pass data around. You can't do complex relationship-based events. And lastly, the simulation behavior between CPU particles and GPU particles is very different, and that can make it difficult to utilize these two systems together. So we began to ask ourselves, what does a theoretical new system look like? Well, clearly we want our artists to be able to build very performant, complex effects. We want them to be able to do things that weren't possible in Cascade. And one of the ways that we've approached that is by making everything programmable and customizable in every direction. That means not only modules, but the emitters themselves, the timing for things. We needed better tools for debugging, visualizing, performance. And we wanted to support arbitrary data from other parts of the engine, as well as external sources. If you have a data that comes from externally, whether it's Houdini or something else, we want to be able to work with that. And we want the users to be able to do almost anything they want. So we're trying to get out of the user's way and let them build content. So we started that with data sharing. And as I mentioned in Cascade, that was extremely limited. So total control over what the particles and simulation are doing is very dependent on the data in that system. So we've made a dramatic change to how we expose data by exposing as much as we possibly can. The position of an actor, it's the emitter's orientation, the time since the system was created, how long it's been running, what color, everything. And there's a huge list here, and there's even more that can be accessed. And all of that ends up in the particle payload. And once we know that we can access all this data, we need to have controls to put it in the particle payload and work with it. And the way we implemented that was through namespaces. The namespace is a container for the data. For example, the emitter's age is contained as emitter.age. So I know that the container of the emitter contains this property called age, or the particle itself may have particle.position or particle.velocity or particle.curl noise. All of this data can be accessed, and you know where that data lives. We call this collection of data, the payload, our parameter map. And this is where all of this is stored. And because we're choosing what data to store, we can also choose what data we don't want. So it gives us the opportunity to reduce the overall particle payload dramatically when that data isn't needed. Data itself is data. It isn't specific to a particle or a skeletal mesh or the environment. It is passed in to the particle payload and can be stored as attributes. This is things like complex U-structs, transform matrices, Boolean flags. We can send anything along for the ride. As long as I can get to the data, I can put it into the particle payload, and then I can use it anywhere inside of the system. So there are a lot of things going on, and we wanted to make this elegant for the end user. And this triggered quite a bit of discussion internally. The engine has examples of both the stack paradigm, which we've used in Cascade, but also this concept of working with graphs from blueprints and our materials and a number of other tools. And both of them have upsides. Graphs give us a lot of control. I can take data apart, I can do custom math, I can put all that back together, I can control the relationship between data. Stacks, on the other hand, are very readable and very easy for users to add them and have their effects implemented. So our solution was to create a hybrid of these two systems, and I'll explain more about that. So we broke it into three main contexts. We have modules. Module is, it speaks to data, meaning it controls how the data is implemented. It encapsulates behavior, such as acceleration or size over time. It stacks with other modules very nicely. We're basically writing functions. If you've used the material editor, you're writing a preset way to manipulate and work with data, and this all works nicely together. The next container are emitters. And the emitters are where you put these modules you've created so that they do things. An emitter is a single-purpose object that can be reused in a number of ways, and it can even be instantiated, so I can have multiple emitters created from this original parent emitter, but then those parameters that are defined in those modules show up at the emitter level, and I can make changes there. I can override the behavior, and that can give me an emitter that does something a little different the next time. And then systems themselves are the outermost container. A system has multiple emitters, or can have multiple emitters. It can override details in the emitters or in the modules. So the modules themselves are where most of the graph logic occurs. You decide what to do with the data, how to manipulate it, and then it's used in the emitters, which implement the stack paradigm. And then those emitters are used in the systems, which also have a stack paradigm, but they have an additional behavior, which is sequencing. This is where we've implemented sequencer within Niagara to allow us to control when and where and how particles will be created and used. So the first thing you'll need to get familiar with Niagara is the creation of modules. So this is a new module being created. On the left, we have the input map, and that's the particle payload. That's everything this particle emitter, or this module, has in terms of data. So we can get that data, and we can set that data, and then we pass it to the output. And that means that what we're doing is basically feeding in data, doing some work with it, and then passing it back out. So my module takes in some amount of information, processes it, and then passes it up to Niagara. We talked about the concept of namespaces, and this is where we start to use those things. For example, here we have an example of our parameter map here, where we have things like module level data, velocity scale, and this is user created. So a designer created that data type in that namespace and said, I'm going to use this in my emitter somewhere, or in my module. So you can see here in the under particles, we have particles.color, .position, .velocity, And that is actually referring to the particles themselves, not the emitters, not the modules, and not the system, but I can actually get individual color or individual behavior from particles. And then, of course, we have other layers as well. So, for example, engine.owner.velocity, that's whatever owns this particle system. If it's attached to, say, a player and he's running, I can actually get the speed that the player is running at and feed that all the way down into my particles. So here we have an example of kind of the world's most simple module. We get the particle's current velocity, and then we also get that module.velocity scale that the designer created. We multiply those two things together, and then we set that back to the particle's velocity. So if this happens when the particle is spawned, it will have that velocity added to it when it's spawned, and then it will be done. And that's where the module usage flags come from here. These module usage flags let me tell the system where I want to be able to use this module. So if I write a module that it makes sense that I could do things over time, then I could have it be part of the particle update script. So every time that particle moves, this script could run. And that would become something like acceleration. Every tick, it looks to see what the particle's current velocity is, modulates it by the velocity scale, and then passes that back in. So it's a very important way of using the system to control how and where these modules can be applied. So here's an example of a module in action. So the input map comes out. We get the particles, the engine's current time, and then we also look at the time for the particle itself, add them together. If it's less than 1 second, then we're looking to continue to pass the particle's velocity along. And then we just set that in the parameter map and it continues. But if the particle's lifetime happens to exceed 1 second, the particle is instead given a velocity of 0, and that's passed through. And in the animated GIF, you can see that happening. As the particles move from left to right, they continue moving until they've lived for at least a second, and then they stop. So this is a kind of manipulated version of over life. And of course, we give you a lot of tools to build these modules with. These are just a sample of some of the logic nodes that you have available to you. And some of these are even functions themselves, such as multiply quaternion. The reason it's a darker blue is because that was a node that one of our designers wrote as a function that could be used inside of the module. We've also added a lot more what we call coercion nodes. These are nodes that allow us to bring data in, change how we perceive it, and then pass it out. Whether that's changing X and Y to Y and X, or changing the order of RGB, all of these can be done within the modules. And at the end of the day, it's all HLSL. All of our graph logic that we build gets passed into an HLSL cross-compiler, which compiles it for either the target GPU platform or SIMD-optimized virtual machine for CPU. Our goal, in as much as it makes sense to do this, is to have complete parity between CPU and GPU, but there are places where that doesn't make sense. For example, on the CPU, I can do line traces to find distances in my world, whereas on the GPU, I have access to the depth buffer. So there are different solutions for problems, and we plan to integrate those both so you have access to whatever simulation data or type that you need. And because it's all HLSL, we decided to expose the ability to write HLSL directly in our modules. So you can write out HLSL, compile it out, it will just become part of the module. So this is what a Niagra emitter looks like. We have the preview in the center left, and on the right we have our module stack here, which is color-coded based on what part of the work is being done. The top orange block is the emitter spawn and update. This controls the emitter's lifetime. Below that we have particle behavior, and that's where modules that affect the particle directly will be placed. We can also turn these off or on. The checkboxes allow me to disable or enable them. I can change the order, get rid of them, and then of course I can expand them out and change the details. Here we have our attribute spreadsheet that shows me all of the data that I have in this particle system to interact with. And then here we have the sequence track for this one emitter. And this just shows me how long it will last, when it will spawn, and things like that. So in looking at the comparison between what a system is versus what an emitter is the core building block for a Niagara system. Systems, being a larger container than the emitters, have their own global user values that can be passed down to the emitters. So if I have, say, an overall velocity multiplier, I can put that in my global system, and then every emitter inside that system can read that global velocity modulator and change based on that. Sequence also own the cadence of each effect, using sequencer to control looping, burst spawning, and also offsets and timing. So this is what a system in Niagara looks like. We have multiple emitters. We have a new system portion of our details panel, which gives me everything my system itself would use. And then this is the sequencer portion of Niagara systems, where we can have multiple emitters all tracked independently, turned on and off to control the animated flow of this effect. One other very important thing that we've done is dissociate the way we render a particle from its simulation behavior. And we do this by adding specific renderers for our particle systems. So in this case, I can have, say, a fast-moving particle that has one renderer that adds a core sprite to it, another renderer that adds a light onto that, and then I could have a third renderer that does the trail behind it, all off of a single particle. So one particle can represent large amounts of data. Now I get to do the live stuff. So this is one of our Niagara systems on a mannequin from UE4. And it's a very pretty, nice system, moving in closely, but I can actually go in and work on some of the modules here, if it'll load. There we go. So this is the exact same module that you saw here, or the exact same system that you see here, but in Niagara, I see that in my particle system, I have a module that hasn't been built out yet. So I'm going to do that now. I'll stop that to get rid of some of the audio. So here's a live version of all of the particle map and other behavior that we've been talking about. So I'll start to build this out. So what we're going to do, right now all of those summoning particles just come in towards the center of the effect. So what I want to do is I want to make them turn into a vortex and spiral in. So the first thing we're going to do is we have each particle's position and their owner's position. And the owner is actually that center of the sphere. So wherever the particle is, I want to know where it is in relation to the center of the effect. So I'm going to subtract these two vectors from one another, which will give me a third vector, which is giving me the direction from the particle to the owner. And then because I don't need the length, I just want the direction, I'm going to normalize that. Now, I have a vector pointing towards the center of the particle system, but I don't want to go straight to the particle system, I want to go around it. So what I'll use is the cross product, which gives me, given two vectors, it gives me the orthogonal vector to those two. I'm going to give the cross product of a user-defined value. So this module.vortex axis was written by the designer. He added that to the particle payload, and because it's in the module, it becomes editable by the user. So I can say what axis around my effect do I want this vortex to happen. So now that we've got the cross product there, we need to do something with it. So I'm going to normalize the distance range between the particle and its owner, and then I want to know what that how to fall off the effect. As I get closer, do I want to go more in a spiral, or do I want to lose control and go inward? So we'll use another value, the module influence fall-off radius, to control that. So now I'm getting the normalized range from a fall-off from the sphere to the particle, so I know how far it is and how strongly to influence it. So jumping past that, inheritance is an extremely important thing for us. We looked at how we were building effects in something like Cascade, and we realized we were rebuilding very similar effects very frequently. We were building essentially the same explosion, the same spark, the same muzzle flash over and over again, because there was no good way to inherit any of these things that we created. There was no way to share them. So that's been an extremely important part of our particle systems here. We've decided that full inheritance support is a tentpole feature of Niagara. So I talked a little bit about overrides. Anything that a child inherits from its parent can be overridden. So I can choose to change those values, revert them back, or completely disable that particular module if I want. You can do this at the emitter level, at the module level, wherever I want. Another important feature of inheritance is the ability to create dynamic inputs. You essentially are able to create an input control that the users can work with that may be doing much more complex logic, much more complex logic under the covers. And again, all of this is HLSL. So we've added the ability to convert inline to HLSL. So if you choose to say, I want to write a custom script for my velocity instead of just setting a value, you can actually do that right there. It will convert it for you, and then you can modify it. So it's really good for occasional things that you may want to implement. Well, it would help if I wasn't running the engine twice. So I'm going to do a live demonstration of some of the modularity that we're building into Niagara. I enjoy waiting. Yes, I was lying. All right, so this is an explosion effect created in Niagara. And it's made up of a number of emitters. We've got ones that do debris, trails behind the debris, the central explosion burst, and some animated smoke that wafts around. If I move over, here are those individual pieces spaced out, so you can actually see the three components that make up this effect. So what we challenged our designers to do was to take each of these three emitters and make a bunch of variations in 5 minutes. So these are all the exact same three systems with overrides in place modifying how they behave. They're faster, slower, constant, burst, cloudy, smoky. All of these made using 3 emitters. No additional custom work, just tuning the values in those 3 emitters. I don't use PowerPoint that much. So, events. Events are extremely powerful. Because of the way we can encode into a payload, we can send any amount of data from one particle system to another within Niagara. We can even run that directly on a single particle by its ID and know that that particle will maintain that ID as long as it lives. So, for example, here's what the event system looks like. I can write this event and say, here's the location. I've reached some position, pass this data across. And then the event handler inside of the emitter can take that data and execute something else with it at any time. I can do way more complicated things than just spawning a few particles. Or I can spawn one particle, or I can spawn particles that are based on the velocity of the particles during that event. Because again, I have access to the data, and the data is arbitrary. As long as I know what to do with it, I can do really cool stuff. So data interfaces are how we bring external or internal data into Niagara and allow us to work with it. This could be meshes, audio, external derived data, code objects, text, whatever. We can write these as plugins, so we can expand this in the future as we find other data sources, things that we can't even consider what they might be now. We can expand those later on and have a lot of power come into the system. So for example, here's some of the data interfaces that we get for skeletal meshes. If you're familiar with Cascade, our skeletal mesh information is pretty limited. We can get bones and triangle data, but we don't have a lot of complex data coming to us from that. So now we have access to almost everything. So now I'm going to show what some of our artists were able to put together using these data. That's certainly something that would have been impossible to do in Cascade or in any other way prior to this. So, what are we doing in the future? The full suite of modules that we've already built will be available, and we'll be building more. We'll be continuing to expand to additional data interfaces as we work with our partners, licensees, to find out what kind of data people want. We'll be implementing more tools for scalability and debugging, and in-viewport controls and programmable widgets for being able to manipulate how your simulation works directly in the world. And this will all be available as an experimental early access feature in 4.20. So before we get to questions, there's actually one other really nice effect that the slide for it didn't make it, but I wanted everybody to see it because I think it looks really good. One of our artists worked to make a single Niagara system that could do an entire rooms full of effects. So Niagara is controlling the motion of the spheres, the electrical arcs, the distance at which it can strike. It's finding vertices on these objects to hit based on how close they are. All of this is being done using all of that arbitrary data that we can now bring in as part of Niagara. So it looks like we have gotten to the questions portion of our talk. So if anyone would like to ask questions, I would love to try and answer them.
inheritance에 대해서 다시 한번 설명해 주실 수 있나요?
Okay, so in Cascade, if I made an effect, the only way for me to get more use out of that effect would be to copy it and then make changes. Inheritance basically means that I can treat emitters as I would a material instance. Instead of duplicating them into a new Niagara system, I can just instantiate it and modify its properties without creating a new one from scratch. And if I make changes to its parent, the children will inherit those changes, which was not possible in Cascade.
기존의 캐스케이드 파일들을 이제 나오는 나이아가라에서 쉽게 이주가 가능한지, 지금 기본적으로 나이아가라에서 쓸 수 있는 모듈들이 기존의 블루프린트에서 쓸 수 있는 내용들과 좀 겹치는 부분이 있어 보여요. 그래서 나이아가라에서 할 수 있는 것들을 지금 이미 블루프린트에서 할 수 있는 것과 어떤 차이점이 있는지 궁금합니다.
Sure. So Niagara compiles everything down to HLSL. Blueprints compile down to a virtual machine and execute as code. It's a very different system. We just use a very similar editing paradigm for creating them. So while the graphs look very similar, the data they're creating is very, very different. And as far as Cascade, the intention is for us to provide modules that are very similar to Cascade behavior so that you can recreate Cascade particle systems closely in Niagara. We may have a conversion in the future, but we have no plans right now for that. The systems are different enough that you will be able to use materials and meshes, but the actual logic from Cascade will not carry over to Niagara, not directly. All right, thank you very much. I hope it was entertaining. I apologize for not getting one portion of the demo correct.